the KL divergence. Okay, so which has a simple formula. So dKL of this is basically P of x log of P of x over P of y as an example, right? Okay, so because, so let's go back over here. Okay, because the actual distribution is P0 given x, we want to approximate it by QZX. How would we know that this approximation is good or not? We'll take the KL divergence of these two. Okay, so this is what I wrote over here, KL divergence of QZ given x with PZX, which is the actual that we are trying to approximate, right? Makes sense? According to the formula for the KL divergence, this is this term multiplied by log of this divided by this, so this term, log of this divided by the second term. Okay, everybody sees? Just a simple statement of the KL divergence formula, nothing else, okay? Okay, now let's expand this further. Okay, now if you recall, so far hopefully everybody sees that, right? Now recall one more concept. So if you are given, let's say, expectation of x is basically summation x p of x. Okay, so if you take a look at, for example, this part over here, you'll see there's, so think of this like x. Think of this, because this is with respect to the variable z, right? So think of this whole thing like the probability, like p of x in the expectation formula, right? So basically, just like if I had x p of x, I could write this as equal to expectation of x. Very similarly, this whole thing could be written as the expectation of just this term, okay? And of course, with respect to z. Okay, so anyway, the KL divergence became the expectation of this term, okay, which is easy to see. Now, in the log, if we do the log of a divided by log of b is simply first term minus the second term, correct? Okay, so to summarize, all we have done so far is we've expressed the actual distribution with what we will try to approximate by. The KL divergence, we have said, will be this part over here, expectation of log of QZ over X minus log of PZX. Okay, now what we'll do is we'll apply the Bayes rule to further try to understand or make it into a form that we can use in our code. Okay, so let's focus on now just this PZX. So according to the Bayes rule, PZX is XZZ over P of X, right? So then basically this part got expanded by the Bayes rule, right? Okay, now let's go further. Can we do a minus P of X over there?
Yeah.
So as you can see, this is the same thing. Multiplication turns into an addition once we are doing the log, correct? So log of PXZ, XZ, then log of PZ minus log of X. Okay. So this became, so anyway, as we expanded by Bayes' rule and then further expanded the log, this is what happened to the KL divergence between these two, right? Okay, so Now let's go further. Okay, so then all we are doing is distributing this minus. So then this became minus, this became minus, and this minus became plus, right? Okay, now we were doing the expectation with respect to z. Okay, so that means the p of x over here is a constant. It's not varying with respect to z, so we can take that out. So basically, this expectation was over, see, it's like this. Expectation of 2 is basically 2. For any constant, it doesn't change, right? So log px went outside of the expectation term. Okay, now next thing we'll do is move the log px on the other side. So from here, we moved the log px on this side, so it became negative. And this is same as the right side, so nothing special so far. Okay, then what we did is we multiplied both sides by negative and put the log px over here. So minus became plus, this became minus, right? And everything over here got multiplied by the negative term. Okay, so as we multiplied it by the negative term, so take a look at this part now. Okay, remember in the beginning when we were describing the KL divergence, we had expanded it to the difference of two logs. So essentially, by the definition of KL divergence, log of QZX, log of PZ is nothing but the KL divergence between this and this. Okay. If you're not sure, see, let's try to explain Q of ZX, KL divergence with PZ. Wouldn't that be QZX, sorry, ZX, then log of QZX divided by the second one, which is P of Z, right? And this is what we were writing as the expectation of QZ given X log of, so this is expectation of log of QZX over P of C, right? And if it's A log of A divided by log of B, isn't it A log of A minus B? And that's what we had over here. So what I'm trying to say is this is nothing but the KL divergence of these two quantities. So that becomes dKL of, right? So anyway, in the next part over here, okay, we basically replace this part by the dKL divergence, KL divergence of these two. So this is a very important equation. Okay, now let me show you a couple of interesting properties. We talked about it last time. Okay, but let me refresh your memory. KL divergence between two distributions, first of all, is always positive. Okay, and also it is not symmetric, meaning QP is not equal to the KL divergence between P and Q. Okay, so it's asymmetric. But for right now, all we care about is the fact that this is always positive. Okay, so up to here, hopefully everybody sees it was nothing but started with the KL divergence between the actual and what we wanted to hope it follow. And then by applying Bayes' theorem and expanding it into the expectation form, this is what we came up with. Okay, now let me see if you follow it. So from this equation, okay, suppose I take the log to the other side. So if I wrote DKL of
minus
QZ given X with PZ given X. Okay, and I'm moving log to the other side. So then this will become E of log of Px given Z minus DKL QZ given X with P of Z
minus log
and minus this log of Px. Correct? So all I did once again was move log Px to the other side. Okay. And I have a negative term over here. So if I multiply both sides by a negative, wouldn't this become,
negative E log
this will become log, so this negative will become positive, right? So log of P of X negative, this whole thing. Correct? And this negative will go away because okay, so this is equal to this. Right? So once again, all I did is move Px to the other side, multiplied by negative on both sides. Now this is the key equation for variational autoencoders. Okay? Why? Okay, let me give you the idea. Can this be negative?
no
This is given to be always positive. You guys agree? If this is positive, if you take a look over here, there's a negative term involved over here. So what does that mean? This has to be bigger than this one. So the implication of this is log of Px has to be greater than equal to expectation of log of Px given Z minus DKL of QZ given X or P of Z. And why is that? Once again, because we know the left-hand side was this, which is positive, so this has to be greater than this. Okay? In generative models, what do we try to maximize?
the model parameters
Remember I started with P of X1, X, and given theta, right? Then we turned into a log so that it turns into a sum. So don't we try to maximize log of P of X? So that's the goal in generative model. Any model that gives us the highest value is the best model. You guys agree? So now try to understand this equation. Okay, this equation is saying for us, for this to be maximum, okay, first of all, it has to be greater than this. So maximizing this, won't it automatically mean maximize this? The right-hand side. Okay, so the technical term for this right-hand side, because the left-hand side is like evidence. Remember, as I mentioned in the probability Bayes rule, so this is our evidence. So basically, this is called the evidence lower bound. Okay, often expressed as ELBO. So anyway, the summary of all of this is we want to create a variational autoencoder, right? Okay, so here's the encoder. Here's some Z, here's some X, here's X bar. Okay, so the question is, there's a model associated with it, right? How do we know what would be the best model? So not only we want to make recovered X similar to X, we also want to force this to a distribution so that we can sample from it, okay? So as we went through all of this math, we discussed that we don't know Px given Z. Because if we know that, then it's trivial problem. Just sample from it and generate new data. Okay, we don't know this. Since we don't know this, then as we went through the math, we came up with the evidence lower bound equation. Now this is very easy to see, okay? If you take a look over here, suppose we make this normal distribution. So our target will be to make P of Z normal, okay? And what is QZ of X? Isn't that, we discussed that's the output of our model? So we are saying output of our model will follow normal
the
distribution, right? Okay, now what is this part over here?
Is it like?
Okay, if this is Z, right? Then won't it be P of X given Z on the output? See, just like I said, if this is X, this is P of X given Z. So obviously this will be P of, oops, my mistake, P of Z given X. So based on X, we generate a hidden variable, right? Okay, here based on Z, we recreate the output. So this is basically the reconstructed output. Okay, so anyway, take a look over here. What's this part over here? Reconstructed output, right? And we always try to, the log of data is the same as enhancing the normal product of probabilities, right? So essentially, this basically tells us the reconstructed output. Okay, follows the model. So the two terms, I erased it over here. If you recall, we had written in plain English what our goal was. Our goal was make the hidden space follow our distribution. So which, if we try to minimize this, because if we try to minimize this, automatically this term will get bigger because we want to maximize this term, right? So KL divergence produces a minimum value if the two distributions are equal. So if we make this normal, then we will be able to accomplish forcing this to follow a normal distribution. Then we can easily sample from it. And this part essentially tells us the reconstructed data from Z has the highest log likelihood, meaning the reconstruction is as good as possible. So VAE will do, once again, two goals. Reconstruction will be similar to this because of this term. And lastly, this will follow a known distribution P of C. Okay? So that's why I was saying, whoever came up with this, to me, it's brilliant. I mean, it took me a long time to really understand why it's, and as you can see, there are a lot of concepts coming together over here, right? So I highly encourage you to go through a couple of times, convince yourself this is our final answer, which I put on the next time, right? Okay, still one thing that we need to still do is we need to put this in code, right? This equation in code. So the question is, how will this be put in code? Okay. So to show you that, so once again, keep in mind this. We know we can pick a known distribution, such as normal distribution for this one. This is whatever is output being produced in our hidden space. So, okay, so again, there's another, I'm just giving you the, okay, so on the second page, if you take a look, okay, so the second part of this evidence lower bound was we wanted to make QZ given X similar to P of Z, and this will be normal distribution, as an example. It could be some other distribution also, but for the case of normal distribution, people have done further evaluation of this term and have found that, as I say over here, if we want QZX to be Gaussian with parameters some mu, in higher dimensions the variance is like a covariance, so the sigma is the covariance. Okay, then it can be computed in closed form, so the DKL of a normal distribution, so this is normal with a given mu and covariance happens to be trace is like the sum of the diagonal terms, then mu x transpose mu x minus k minus the log of the determinant. Anyway, if we go further a little bit, there's a further simplification for it. So the final answer is, this is what we'll program. So KL divergence between a given distribution with some mu, some covariance in higher dimensions, with the normal distribution can be written like this. Okay. And like I said, last comment over here. So even though we had a log term over here, so we typically use e raised power, so then this gets reduced to over here. Okay. Okay, so let me summarize the whole thing, and like I said, try to go through it a couple of times yourself, make sure it's making sense. Okay, so the first important concept was we wanted to accomplish two goals. We wanted the reconstruction to be as good as the original reconstruction from the compressed data, right? Okay, second goal was we wanted this to follow a known distribution so that later on we can remove the encoder, sample it, produce artificial data. Okay, so we started out by expressing the similarity between this and some target. So this is some target, QZ of X, which is produced by the encoder. Okay. The KL divergence between these two, then we applied the Bayes theorem, and by manipulating the equations, this was our final conclusion that log P of X has to be greater than these two terms, either DKL of Q of C was QZ given X with P of C. Okay, so as you can see, if this is normal, then whatever this distribution is, if we try to minimize this, will make this normal. And lastly, this term, if we try to maximize this term, we'll make sure that our reconstructed data is similar to our input. Okay. Okay, so now we'll program it, and once I show you the code, you will see it will be exactly implementing this equation and trying to maximize this. And then once it's trained, we'll be able to sample new data from P of Z from the normal distribution and generate artificial data. Okay. So now let's go, how do we program? So let me turn this up. Okay, so now let's take a look at programming. Oh, that's... Okay, see, we want to be able to come up with our own new deep learning models and be able to evaluate and see how good or how bad they are, right? So one option would be, like you guys have learned in this course, create an architecture. So it doesn't matter how complicated the architecture is, right? We feed in some data, it produces some, in case of generative models, it will produce similar X, right? Then we do the back propagation. And we adjust the gradients. We have already defined a loss function over here, which, as I showed you before, had two terms. One was trying to minimize the KL divergence between P of Z and Q of Z given X. And the other was trying to maximize the log of the expectation of X given Z, meaning from the compressed data, we can recover X as nicely as possible, right? Okay, so we can literally go through, compute the derivatives of this loss function, backpropagate it, make it work, right? The only problem is, you know, just like you guys are programming CNN, it will take us, of course, we'll make mistakes in programming, so it will take us a while for it to really work. So from now on, I'll give you the cleanest, best way so that we can keep our creativity and yet verify it in a very, very short time. Okay, so now I'll introduce TensorFlow to you. Not from the point of view of, you know, here's data, put it in, it will classify and you get 98% or 95% and you are done. But our goal in this course, like I said, is from the point of view of if I ask you, change this model in this way, and obviously there won't be any examples on the internet that you can copy and so how do we use TensorFlow for that purpose? Okay, so TensorFlow has a couple of ways to program it. Okay, one is called the Graph API. And one is, there's a high-level library, Keras, which is built on top of the Graph API. Okay, Keras is extremely easy. Even non-technical people these days are using Keras as long as you know how to, you know, set it up, feed the data, train it, and test it. So it doesn't even require, in my opinion, more than high school information, right? But to understand it, of course, what it's doing, we do need, right? So you guys will be rarely using Keras in this course. You'll be using the Graph API so that we can set up our whole architecture and backpropagate it and make it work, right? So there's some key concepts in the Graph API. And I've created already a handout. I forgot to put it before coming over here. And in fact, I'll refine it a little bit. So then I will show you, using the Graph API, for example, how do we program BAE? how do we program, for example, Siamese networks that we talked about? How do we program regular NN and deep CNN? Now, to save time, let me add this. If it is a standard architecture, let's say a CNN, okay, then go ahead use Keras. Okay, why make your life harder? As long as you understand it, okay, what it's doing. But if you're investigating, you know, for example, we discussed over here our loss function, the evidence lower bound, right? P of x was trying to make it bigger, and there were two terms over here. Okay, one term, if you recall, was trying to make reconstruction as good as input, correct? What was the second term trying to do over here?
Fitting into the normal, I mean, any
Make
distribution.
q z of x follow normal distribution, so that we can sample from it later on and generate artificial data. Okay, what will happen? Like, for example, you may be curious, okay, what if we give more weight to this reconstruction? We multiply 0.8 over here. We multiply 0.2 over here, right? So what effect will it have? Of course, the reconstruction images or whatever numbers will be very, very good. But if we try to sample an unknown, so if we, here's z, here's p of x given z, right? So if we sample something from here after it's trained, if it was trained on this type of loss function, what will it? It will do a really good reconstruction, right? Of an input. But if we sample from, will it do a good job? No, because now QZ of x is not really following a normal distribution. So if we are sampling for normal, it may not even look like a meaningful data. Okay. So anyway, those are the things that I will show you so that we can, using TensorFlow, be very good at it and create our own architectures and use it. Okay. So here's the neat thing about TensorFlow. So TensorFlow Graph API. Okay, so first of all, we define our model as a sequence of computations. Okay, so to give you a very simple example, suppose you wanted to create a neural network, right? So you will have an input x, okay? Then this will feed into some kind of a weight matrix. Suppose, right? And suppose we're adding bias over here. So then suppose there's an activation function. Then suppose there's W2. Then there's a B2, B1. Then there's an activation function, and suppose this is the output.